What is up, guys? Okay, now continuing on our work with biochemistry, we have our titration curve right here. Last time we learned about the Henderson-Hasselbalch equation involving pH, proton concentration, pK, equilibrium constant for ionization, and midpoint. Now we're going to be learning about some of the titration curves. So here is a titration curve of acetic acid. A titration curve is a plot of the pH of a week. Let me just try and fix that right there. Bit of a mess up right there. Oh. Oops, that's the wrong symbol. Let's try this. Of a week. That's not working too. Let's go for a pencil. Of a week. Plot of the titration curve, plot of the pH of a weak acid. So shown here is the plot of a weak acid. 0.1 molarity CH3COOH against I didn't finish this. Who made this? Against the degree of neutralization of the acid by a strong base. So this is our strong base, 0.1 molarity sodium hydroxide, and this is our weak acid. As more of the strong base is added, more weak acid is converted to its conjugate base. A buffer system follows the Henderson-Hasselbalch equation is formed. So there is our Henderson-Hasselbalch equation. pH is equal to pKa for a weak acid. This is the buffering region. Here is our weak acid. And as we go down this line, hydroxide or our strong base is being added. Okay. And then as more base is added, it loses a hydrogen to become what is called the conjugate base. I apologize, my dog is making a lot of sounds. But we will continue with this video. Let me try and calm my dog into here. Gucci! Oh, and here comes my dog. And she is licking my feet. Okay, at least she stopped barking at our door. Okay, now continuing on with buffers. So buffers consists of a weak acid and its conjugate base. So similar to what we learned up here. Weak acid and its conjugate base. That's how we get our buffer. So the roles include resisting the changes in pH when acids and bases are added. Maximum buffering capacity occurs at a pH equal to the pKa, but a conjugate acid-base pair can still serve as an effective buffer. when the pH of a solution is within approximately plus or minus positive or negative 1 pH unit of the pKa. At the pH, when the pH is less than the pKa, the protonated acid forms this, and that is the predominant species. Let me see if there's a name for this actually. Okay. So when the pH is greater than the pKa, the deprotonated base forms this, our conjugate base. This is the predominant species in the solution. The bicarbonate buffer system is the major buffer of plasma and interstitial fluids. So this is the buffer system. You can see carbonic acid right there. Amino acids can act as acids and bases. Okay. So we have our non-ionic form, which has no positive or negative charge, and we have our Zwitter ionic form, which has both a positive and negative charge. So these are amino acids. So alpha COOH, there's our alpha COOH. So by alpha they meant, oh, my dog is trying to attack the door. I'll be right back. Gucci! Gucci, come! Okay. And there comes my dog. Good girl. Stay. Gucci, stay. Gucci, stay. 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 Gucci! Oh, man. She does not like to listen. I apologize for that. Continuing on, we have alpha, and NH3 is added next. There is our NH3. An amino acid is dissolved in water. It exists in solution as the dipolar ion or Zwitter ionic forms. So Zwitter ionic, once again, is a form that has both positively and negatively charged. Here, notice the difference in pKa of these two. For COOH, this is the pKa in this range. And for this, when an amino group is added, pKa is like that. Substances having this dual nature are amphoteric. Now, let's find out what amphoteric is exactly. Of a compound, especially a metal oxide or hydroxide, able to react both as a base and as an acid. Okay, that makes sense. Let's just put that right here. So definition. Let's try and put an arrow to this definition. Let's highlight it. Okay, moving on, acid-base properties of glycine. To start with the structure of glycine in strongly acidic solution. An example would be, and we talked about glycine before. We talked about it in the previous video about it being the main exception because it doesn't have a positive and negative charge. So it's strongly acidic in solution at pH is 1. It exists in a protonated form, so alpha amino group, because an alpha amino group is protonated. There is a charge. As the pH is raised, which is the first proton to be removed, hence respective pKa's. The more acidic proton belongs to the CO2H group. It is the first one removed as the pH is raised. Okay, so that's the first one removed as the pH is raised. So here is a typical ammonium ion with a pK approximately 9. Here's a typical carboxylic acid, pKa from 3 to 5. So let me just highlight that for you guys. There's the ammonium. And here is the carboxylic acid. I'm gonna call my dog real quick. Gucci! Gucci! Gucci, come! And my dog isn't coming. Okay, that's fine. So for ammonium, the pKa is at 9. For carboxylic acid, the pKa is from 3 to 5. These are some of the acid-base properties. My dog is here. These are some of the acid-base properties of glycine. A proton attached to the N in the Zwitter ionic form of nitrogen can be removed as the pH is increased further. So here is an example. So this is a Zwitter ionic, as you can tell by positive and negative charge. There is our N, and as you can see, it has some protons or hydrogens attached to it. Now, the difference is, what we're doing here is let me just type it in, adding more base, and what that does, and what that does is it increases our pH, making it more basic. So pH is increased further. So as you can see over here, this nitrogen has now lost one of its protons, increasing the pH. The pKa for removal of this proton is 9.60. Okay. This value is about the same as that for NH4+, which is 9.3. So this is more acidic than this. So this is more basic. It is much higher. Because this is more protons, so it's more acidic. Okay, now we're going to be learning about the titration curve of glycine. So, adding sodium hydroxide or strong base yields two titration. Oh, this one has two titration curves. So the first curve here as 0.5 equivalents of base hydroxide is added, the pH is equal to the first pK, which is 2.34. For glycine is equal to the positive. pK1 is a carboxyl group. So there is our carboxyl group, pK1. Let me just type that in real quick. Carboxyl group. There we go. Okay. pK1 is the carboxyl group. As 1.0 equivalents of hydroxide is added, full titration of the first hydrogen occurs at pH 5.97. Full titration of the first H+. Glycine standard. So from my chemistry class I learned that this circle apostrophe symbol right here is standard, stands for standard, so this, I'm assuming this is standard glycine. So standard glycine is the predominating species. At 1.5 equivalents, OH minus is added, base is added, at pH is equal to pK2 at 9.60. So once more base is added, we reach this point. At 2.0 equivalents of hydroxide added, full titration of the second proton, glycine in the predominant form. Glycine with a minus sign is the predominant form. Before it was glycine standard is the predominant form, now it's glycine with this minus sign being the predominant form. Okay. Now we're moving on to ionic forms of no longer glycine but alanine. So you can see here pH 1 to 2, pH 3 to 8, and pH 9 to 12. As we add more OH, you can see the pH is changing. Adding more base basically changes the pH and it decreases our pKa's. Alanine is an acid solution, so its pH is less than 2. At low pH, approximately 1, alpha amino groups are protonated, whereas alpha carboxyl remains unaffected. Thereby the net charge is +1. As the pH of the solution is raised, the carboxyl group can dissociate by donating a proton and form COO-. This form is also called a Zwitter ion. In this case, the net charge is 0. Okay. So originally, we can see as more OH is added here, this hydrogen was donated, forming this Zwitter ion, because it just had a positive charge before, now it has a positive and a negative charge now. Okay. So the net charge is 0 now here. Oh, and here we have some pKa's of the alpha COOH of this original COH. And the alpha NH3 group has this pK. So as more base is added at a pH greater than 9, I'm just going to highlight the pHs now. So once the pH is greater than 9, the protonated amino group loses a proton. So let's find that proton. Oh, the protonated amino group loses a proton. So this NH2 right here. It lost a proton and now it has no positive charge. Thereby, the net charge is now -1 because we have 1 minus here because of the carboxyl group that lost one of its hydrogens. So the net charge is -1. Okay? And that is alanine. So here is an overview, the acidic and basic amino acids. The acidic amino acids, aspartate and glutamate, have carboxylic acid groups that carry a negative charge at physiological pH. So aspartate right there, and glutamate. Good enough. Undo. Try it again. And glutamate have carboxylic acid groups that carry a negative charge at physiological pH. The basic amino acid histidine, lysine, and arginine have side chains containing nitrogen that can be protonated and positively charged at physiological pH. The positive charge allows them to form ionic bonds, electrostatic bonds with negatively charged groups. The acidic and basic amino acid side chains participate in hydrogen bonding and the formation of salt bridges. Let's try and see what a salt bridge is. Salt bridge in electrochemistry is elaborate. Okay. Oh, it's that thing that is involved with movement of electrons. Okay. The acidic and basic amino acid side chains participate in hydrogen bonding formation of salt bridge because of the difference in charges on both sides of the bridge. Okay. So we are going to be having an exam, and this table is important. Table 3.4 will be provided on the exam. So we're probably going to need to know how to use our pKa values of some of these amino acids. Here is our alpha carboxyl group. Here is our alpha amino group. And here is the pKa for any side chains. You can see the charges right there for the pKas. And now here is a titration curve for glutamine. We have a few amino acids that are classed as triprotic. A dissociated proton is their R group. A dissociated proton is their R group. Okay. Now my dog is sitting over there. Thank goodness it stopped yelling at our door. Triprotic amino acids can what is happening to this document? Let me just try and fix it. under physiological conditions it will be charged. Good enough. Okay, so we can see it is triprodic. Notice how all these different resonance structures, PK1, PKR, and PK2, and they all can go back and forth. So very triprodic. So as more base is added, we can see, let me just highlight that here, OH is added across. So as more OH is added, we can see that it loses hydrogens. Let's see what else happening here. This carboxyl group here also lost a hydrogen. Let me just highlight the changes actually, just to make it easier for you guys to notice. And then finally, the amino group is the last one to lose its charge. So this would technically have a net charge of -2. Yep. So here we can see the changes. You can actually see the changes as more base is added. So we can see base equivalents. PK1 2.19, PKR 4.25 here, and for PK2 9.67. So we can see all those pKa changes for glutamate as more base is added. Okay, I think that's all for today, guys. We'll continue the rest of the slides in the next video. Thanks for watching. I'll see you in the next one. Peace.